So we were proving the various compactness theorems, namely the Relic-Kondrasov theorem, which said that in a bounded open set, the Sobolev embeddings, almost all of them are compact embeddings. Except one, namely when P is less than n, W1P in LP star is not compact. Apart from that, all the rest were compact, and we proved it. For the case P bigger than n, it comes directly from the Ascoli-Arzela theorem and the fact that functions in W and P are Helder continuous. For P equals n, we proved it using P less than n, and for P less than n, we used the Frechet-Kolmogorov theorem, which characterized relatively compact sets in LP, analogous to the Ascoli-Arzela theorem. Okay, so now these theorems are very useful when studying partial differential equations, especially nonlinear problems and eigenvalue problems. And now we will see a application of this theorem. So theorem. Omega in Rn, a bounded and connected open set of class C1. Let Pm of omega denote the vector space of all polynomials in the variables x1, xn over omega and of degree less than or equal to m. Let 1 less than or equal to p less than infinity. Let V belong to W m plus 1 p of omega, and let V dot be the equivalence class of V in the quotient space W m plus 1 p of omega by Pm of omega. Equipped with the norm. So this Pm of omega is space of all polynomial degree less than or equal to m, so it is finite dimensional. Therefore, in any Banach space, it is closed. Therefore, Wm plus 1 p omega by Pm omega, the quotient space is well defined, and the class normal canonical norm mod Wm m plus 1 p omega. This is the notation we are using for this, is equal to, this is the definition, infimum over all p tilde in Pm of norm V plus p tilde m plus 1 p omega. So this is the classical norm. This norm, so the theorem is this norm is equivalent to the norm defined by V dot map to mod V m plus 1 p omega. So here you have norm m plus 1 p omega of the infimum of all of that when you add elements of Pm. Now V dot is just, you take any representative of V dot, and then you take the m plus 1 p omega norm of it, and that is a norm which is equivalent to this. That is the content of this theorem. So proof. First of all, we want to show that this is well defined. So if V1 dot equal to V2 dot, this implies that V1 minus V2 belongs to Pm of omega, and that implies that mod V1 minus V2 m plus 1 p omega equal to 0, and therefore you have that mod V1 m plus 1 p omega equal to mod V2 m plus 1 p omega. And therefore it is well defined. It doesn't depend on the representative which you are choosing in the quotient space, so that is fine. So the norm is well defined. And secondly, if you have V mod V m plus 1 p omega equal to 0, so this means that V belongs to Pm of omega because omega is connected. So if the first derivative vanishes, it's a constant. If the second derivative vanishes, it's a polynomial of degree 1. If the third derivative vanishes, it's a polynomial of degree 2, etc. If the m plus 1 order derivative vanishes, then it has to be a polynomial of degree m. That means V dot equal to the 0 element in the quotient space. So therefore, and the converse of course is true, and therefore you have that this defines a norm. So this mod V dot is in fact a norm, so there is no problem about that. Okay. So if so this implies that mod V m plus 1 p omega defines a norm on the quotient space. Okay. So now let us assume that V belongs to W m plus 1 p omega. Then you have let p tilde belong to Pm of omega. It's a polynomial of degree less than or equal to m. Then mod V m plus 1 p omega is the same as mod V plus p tilde m plus 1 p omega, because adding p tilde is in the n plus, it's a polynomial degree m. So now this of course is less than or equal to norm V plus p tilde m plus 1 p omega. And this is true for all p, and therefore this implies that mod V m plus 1 p omega is less than or equal to inf over all p tilde in Pm of omega of norm V plus p tilde m plus 1 p omega, and that by definition is the norm V dot of m plus 1 p omega. So one way inequality we already have. So we want to show that reverse inequality. So to need to show there exists a constant C positive such that the reverse is true. Mod norm V dot m plus 1 p omega is less than or equal to C times mod V m plus 1 p omega. So we will do it by contradiction. So this is a standard method of doing it, and see how the compactness will come into play. So assume star fails. So this is true for every V in W m plus 1 p omega. Okay, this is what we want to show. Okay, so assume that this fails for every C positive. So this is star. So what does it mean? That means even if I take however large an n C I take, there will always be one for which the inequality will fail. So I take C equals n for every n, and therefore for every n there exists Vn tilde in Wm plus 1 p omega such that norm V dot Vn dot V tilde Vn tilde dot m plus 1 p omega is greater than n times mod V n tilde m plus 1 p omega. So we can normalize this. So normalizing, there exists Vn in W m plus 1 p omega such that mod norm Vn tilde Vn dot m plus 1 p omega equal to 1, and mod Vn m plus 1 p omega. Therefore, that is less than 1 by n times this norm, so it goes to 0 as n tends to infinity. So now we have to, so we assume the inequality fails for every constant and we have got a sequence. Now we have to get a contradiction. So without loss of generality, by choosing a suitable representative, we can assume norm Vn m plus 1 p omega is less than or equal to 2, because mod norm Vn dot, which is what is the infimum of all Vn plus p, so p tilde. So we can choose a p tilde suitably such that it's so the infimum is 1, so there must be 1 p tilde for which it will be less than 2. So if we add that to this, nothing changes in all these inequalities, so we can assume that norm Vn is less than or equal to 2 just by the definition of the norm in the quotient space. So now Vn is bounded in W m plus 1 p omega, and so by relic Kondrasov or relic, you have, we will work with the subsequences. There exists a subsequence still indexed by n for convenience, because I will work with that subsequence, so I don't want the original sequence anymore, so there's no need to write a nk and all that. Okay, so we will just we says that a bounded sequence as a convergent subsequence, so Vn converges to V in W m p omega. So we proved the last corollary which we proved is W m plus 1 p, so W m plus 1 p omega to W m p omega is compact, because W 1 p omega to Lp is compact. That is the Relic's theorem, and we iterated it subsequently, and then we have that this is compact. So if you have a bounded sequence, there will be a convergent subsequence in the image, and therefore since it's just the inclusion map, so we have Vn converges to V in W mp omega. So let alpha be a multi-index such that mod alpha equals m plus 1. Okay. So let phi belong to d of omega. Then d alpha Vn goes to 0, because that we know. Because Vn in m plus 1 p omega goes to 0, that means for all the m plus 1th order derivatives, they have to go to 0 in Lp of omega. So you have 0 equals limit n tending to infinity minus 1 to the n plus 1, m plus 1, sorry, because you are taking the derivative, integral on omega Vn d alpha phi dx, and that's equal to minus 1 to, I am using the distribution derivative, so Vn goes to 0, so d alpha Vn goes to 0, that means its action on phi goes to 0, and therefore 0 is equal to this limit, and that is equal to integral minus 1 to omega of V d alpha phi, because Vn goes to V. Okay, so Vn goes to V, so this is the limit, and therefore you have this like this. So you have that. This is true for all phi in d omega, so this implies that d alpha V equal to 0 for all mod alpha equal to m plus 1, and that therefore omega connected again implies that V belongs to Pm of omega. So norm Vn minus V power P m plus 1 omega, P omega, sorry, is nothing but norm Vn minus V norm mp omega power P plus mod Vn minus V m plus 1 P omega. This is just the definition. But V belongs to Pm of omega. So this Vn minus V m plus 1th order derivatives of V will all disappear. So this is equal to norm Vn minus V mp omega power P plus mod Vn m plus 1 P omega. Now this goes to 0 since Vn converges to V in Wmp omega. So you have that, and therefore this goes to 0, and this goes to 0 by the assumption on the subsequence here, and therefore both of these go to 0, and therefore this means that Vn goes to V in W m plus 1 P of omega. And if that happens, then Vn dot must go to V dot, but V dot is 0 since V belongs to Pm of omega. But in W m plus 1 P omega by Pm of omega, but norm Vn dot m plus 1 P omega is 1. That was our definition, assumption. Okay, so, and therefore we have a contradiction, and this completes the proof. So let us, a corollary of this, so let 1 less than or equal to P less than infinity, let omega in Rn bounded open connected set, and pi from W m plus 1 P omega to V continuous linear, where V is a Banach space containing W m plus 1 P omega. So V is a Banach space which contains W m plus P omega, and pi is a function like this. Assume pi of P tilde equals P tilde for every P tilde in Pm of omega. So it preserves all the polynomials. Then there exists a constant which is positive, such that for every V or U in W m plus 1 P omega, we have U minus pi of U in norm of V is less than or equal to C times mod U m plus 1 P omega. Proof. So let P tilde belong to Pm of omega. So norm of U minus pi U in V is equal to norm of U plus P tilde minus pi of U plus P tilde in V, because we are just adding a pi of P tilde equals P tilde. Okay, so this is less than or equal to norm of I minus pi times norm of U plus P tilde in m plus 1 P omega, and this is true for all P, and therefore this is less than or equal to norm of U minus pi U is less than or equal to norm of I minus pi into inf p tilde in p m of omega, norm of u plus p tilde m plus 1 p omega. So now this is the usual norm, and we know that that is less than or equal to c times norm I minus pi mod u m plus 1 p omega. Okay, so that tells you that completes the proof. Okay, now how is this theorem useful? So if m is, so remark, large enough, then by Sobolev embeddings we have w m plus 1 p omega is contained in C of omega bar. Or Ck of omega bar, for it depends for some k. Okay, so we can assume pi is an interpolation operator, Lagrange, Hermite, etc. So there will be, so these interpolation operators means that for some degree they will reproduce polynomials as it is, okay, and any other function they will give you another function here. So the above estimate gives an estimate above inequality, gives an estimate of the interpolation error. That means pi u is the interpolated polynomial operator, and then you get the u minus pi u is the interpolation error. Okay, so this is very useful in numerical analysis, especially in the error analysis of methods like the finite element method. Now we have another consequence of this theorem, which is a very important inequality, is extension of the Poincare inequality. So theorem, this is called the Poincare-Wirtinger inequality. So 1 less than or equal to p less than infinity, omega in Rn, bounded connected set of class C1, then there exists a constant C positive such that for every u in W1p omega we have mod u minus u bar 0p omega, the LP norm is less than or equal to C times mod u 1p omega. Where u bar, you know, is the average, this is equal to 1 by mod omega integral on omega ux dx. Okay. If p is less than n, then mod u minus u bar in 0 p star omega is less than or equal to C times mod u 1p omega. Proof. So we are going to take pi of u equal to u bar. So this is like an interpolation operator. So we have v equals LP of omega. Okay, it contains W1p of omega, and m equal to 0. Okay, we have m equal to 0, and so we have mod u minus pi u 0 p omega is less than or equal to C times mod u 1 p omega. Okay, so this is nothing but u bar. Okay, so we get the inequality right away. If p is less than n, then you have that mod u minus u bar 0 p star omega, this is less than or equal to c times norm u minus u bar 1 p omega by the Sobolev inequality, that is less than or equal to c times mod u minus u bar 0 p omega plus c times mod u minus u bar 1 p omega. Because norm is, again I am using the fact, I am just using the sum of the norms. Actually the definition is power p, but I said that's equivalent to this norm. Okay, now u minus u bar, so the first one, that is less than or equal to c times mod u 1 p omega plus c times mod u 1 p omega. Okay, so you have that, and therefore this is equal to c times mod u 1 p omega. The c's are different, they are not the same c always, so please don't get confused by these calculations. The c is a generic constant, we don't want to write c1, c2, c3, c4, c dash, c double dash and so on. So I am using the same symbol c, it need not be the same throughout the calculations, but it's a constant, that's all. So if you Poincare inequality, so remark, valid in W1P0 omega, any bounded open set. Poincare-Wirtinger is bounded, open, connected, C1 omega, okay, and but it's valid in W1P of omega. Okay, so there's a price we have to pay with this. So another way, another way to state Poincare-Wirtinger is that there exists a constant c positive such that for all v u in W1P of omega, such that integral u dx equal to 0, we have mod u 0 p omega is less than to c times mod u 1 p omega. So this is the analog of the Poincare inequality, LP norm bounded by the H1 norm, but on a condition, namely that the average is 0. Okay, so then we have this. So this